When you're a mechanical engineer and you have access to great CAD programs and a cutting-edge 3D printer, what's the best way to fix the busted blinker on your motorcycle? For Ben, one of our staff engineers, it was to use new Topology Optimization features in Annex CAD to design and improve upon the original part. When Ben bought the bike, the front right blinker was broken after it smacked into a branch. He knew from the original owner the part broke often, and so making the part himself was a combination of both fun and held some cost savings. It was also a good opportunity to add some personality to his bike. Ben took the broken blinker and gathered core critical dimensions from it. He built the CAD in Annex 12 and figured Topology Optimization was a good fit to improve the design, reduce the weight, and improve the strength. Because of the nature of additive manufacturing, he figured the flexibility of 3D printing could make up for its reduced material strength. Using our in-house Carbon M2, Ben printed the part in a few iterations, improving upon the design each time. The M2 prints from a resin tank without interruption using a DLS process, making parts similar to traditional injection molding. After an unfortunate safety laydown of the bike, the blinker broke. This time, our in-house CAD guru Matt Martin decided to take a crack at the design and prepared this handy walkthrough tutorial on the process.
Today I'd like to talk a little bit about topology optimization and a real-world project. An engineer in our office broke a turn signal off his motorcycle and decided to use some topology optimization, and this is what he came up with. It's a pretty slick, cool design. I want to show how we got here. I'm going to reverse to go back to where it was originally and show you from the Topology Optimization tab. Go back to Manage Bodies and Manage Optimization Features. You can tell it to auto add all recognized features. Things that it doesn't add in automatically, you can add in manually. To just go through the list here, there's a keep in zone, which is the tube that lets the wire run into the housing. The housing itself is a keep in. The air volume of the housing is a keep out. We don't want topology optimization to be working there. Same with the screw boss that's inside there. There's the attachment screw to the motorcycle. We want to be able to have access to that. We don't want anything to be in the way. And the boss, this turn signal actually fits into a little socket. So you want to make sure that there's nothing on the outside of this. The tube, since it is supposed to be a tube, we want to make sure that there's a keep out zone that's on the inside of that tube to keep topology optimization from doing anything inside the zone. And then of course there's the base itself, and that's a fixed constraint. We don't want that moving around or doing anything. Come down here to manage load cases. Load case, there's really no load cases on this part other than gravity and air resistance. If you think about a motorcycle going down the road, the air would be pushing against it this way. He did set it to 10 pounds force, which is pretty high, which could account for some of the how it looks on the in the end. Last one I always check is the manage design constraints, and there are no design constraints in here, and I'll discuss those as I go through the next part. So that if I reverse the blank on this, you see that this is what it came up with. You kind of see in here the keep out zone that it honored for the screw to attach it to the motorcycle. On the analysis tab, there are some checks you can run on here. So there's design validation for additive manufacturing. So I'm going to do a wholly enclosed volume, check that body, and look at my checkmate here. It does check. It is a wholly enclosed volume. It passed the test. There's no internal voids to this part. Another one I like to run on here is a minimum wall thickness. And tell it to calculate the thickness on there. This will run for a second or so. And then it tells you the areas that you're below your minimum wall thickness, which is set to 15 thou. If I switch my shading here, you can see that a lot of these are just facets that are sitting on the surface. There could be something that you've got an extra facet that sits on top of the surface here that looks like there's, I don't know, a little bit of weirdness that's going on right here in these zones. Something to watch out for when you're running topology optimization for sure. And we'll see what this looks like in the next part. So again, he let me run optimization again. So on the part that I reran, I go down to topology optimization. I left all the constraints the same. I did do a minor change of the way the screw attaches to the motorcycle. with approval, of course. Under Manage Bodies, select the 34. Optimization features. One thing I did do is I left all the optimization features the same. And then under Manage Load Cases, what I did with Extrude 17 is I dropped that down to a little bit more reasonable value. Still about 160 miles an hour, but that's all right. And then under Manage Design Constraints, I turned on Material Spreading. And then that Material Spreading, up to 100% tends to spread into strut-like structures. Above 60, it tends to produce thin wall structures. So I'm a little bit in between that at 90%. And when that's all run, everything is ready to go for my Manage Bodies. I can assign materials. Again, it's just ABS. Manage Load Cases, I can turn on gravity. You can also turn on the global temperature. So if it's in a hot environment or a really cold environment, you can adjust for that. And set up optimization. This is where you're going to actually start running the optimization. So this little slider here does adjust how slow or fine it is. So down here it's fast, but also pretty coarse. Then up here at the other end, it's very fine, but also takes a long time. It's going to take some time to get used to this slider here and how much it's going to take to run your optimization. I can tell it to estimate optimization parameters. And it goes through, it tells me that between 0.33 and 0.05 pounds mass. So I set a mass target of 0.06 rather. Then I tell it to run optimization. It takes me over to this convergent window and goes through with a log file that tells you what it's doing. It's initializing, you'll see meshing, it'll be doing a few other things here, and you'll see the bars do their thing. I'm going to cut out a lot of this. Because it does just take a lot of time to run. And at the end of the convergence, this is what I ended up with. Sorry if my voice is cracking a little bit. I'm just getting over a cold here. So looks much, well, I don't know, cleaner. Looks a lot cooler for sure. It's got a lot more thin wall structures. I'll go back to my analysis, wholly enclosed volume, do a check on that. It does pass. And then I'm going to do my wall thickness check again, have it calculate that. Again, I've got the sharp features down here, but I still have a few facets out here on the ends that I should probably take a look at. But for now, I'm going to let it roll, let it run. I'm going to take a look at how the facets are all lining up in here. So switch this to turn on the facet edges. And you see a cool view of how this is all put together. If I take a look at my maximum displacement, maximum stress, take a look at displacement first. Maximum displacement, very small. Maximum stress, again, very small. So I could turn those on to see the heat maps. Turn off my faceting on there. This also still has almost like little notches where the extrude came out. The keep out area came. One of the things I did is I used my reverse engineering tab here to do some cleanup. This little step here, I probably could have gone back and rerun the optimization on it to just kind of make this more of a tubular strut instead of having it have that step in it. It still has plenty of room to get a screw inside the screw hole. Again, with authorization from the guy who wants to put this on his motorcycle. Was able to clean this up using my reverse engineering tools shown here.